material balances involving combustion reactions. Very often biotechnology technicians would face the problem of going through the calculations for the combustion process using the biomass. Therefore, it is critical to learn the basic terms and definitions related to the combustion processes, as well as to go through set of the sample mass balance problems involving the combustion reactions. When we talk about the combustion process, we basically are oxidizing the biomass or oxidizing the organic matter, and we will be producing, depending on the type of the combustion process, carbon monoxide, carbon dioxide, and water. The inputs into the combustion process include the sources of carbon, hydrogen, sulfur. We have two types of the reactions. We have complete combustion and incomplete combustion. Depending on the type of the process, we will be producing carbon dioxide and water. So if we have a complete combustion, here we have an example of the 1 mole of the propane would react with the oxygen, and as the result of this combustion process, we will produce 3 moles of carbon dioxide and 4 moles of water. Here we have only carbon dioxide, which indicates that this process would be a complete combustion. If we do not have sufficient amount of the oxygen fed into the process, we would end up with the incomplete combustion, and incomplete combustion process would produce the carbon dioxide and carbon monoxide. For majority of the combustion processes, we will be using air as the source of the oxygen, and we should know that the molar composition of air is 21 mole% of the oxygen and 79 mole% of the nitrogen. Product gas is very often called the stack gas or the flue gas. The calculations can be done in reference to the dry basis or in reference to the wet basis. So when we talk about the dry basis, it would be a composition that excludes the water as opposed to the wet basis. An example of the calculations of the composition on the dry basis would be a gas which is composed of 40% of A, 40% of B, and 20% of water. On the wet basis would have a composition on the dry basis that will be equal to 50% of A and 50% of B. When we remove this 20% of water, we are left with 40 and 40%, which contributes as the 50% and 50% on the dry basis. In mass balance calculations, including the combustion processes, we have new definitions that would be required to know in order to solve the mass balance problems with the combustion. Theoretical oxygen is defined as the number of moles of oxygen that is required by the stoichiometry for the complete combustion process. Sometimes the problem can give us information about the theoretical air that is needed for the combustion process. So the theoretical air is defined as the quantity of air that contains theoretical oxygen. When we go back to the previous slide, we know that the composition of air on the molar basis is 21 mole% of O2 and 79 mole% of N2. In order to have complete combustion process, we will be feeding air or oxygen into the process in excess. Definition of the excess oxygen is the amount of the oxygen in excess of that is required for the complete combustion. So excess of the oxygen would be that amount of the oxygen that we have above the quantity that is required from the balanced stoichiometric equation. In order to understand the combustion process calculations, to be able to go through the mass balance calculations for the combustion process, we will go and try to solve the 3 following problems in the next video recording. So the first problem is 100 moles per hour of butane and 5000 moles per hour of air are fed into the combustion reactor. Calculate the percent excess of air. The next problem: methane is combusted with oxygen to yield carbon dioxide and water. If we have 100 kilograms per hour of methane in the combustion process and oxygen is present such that there is a 15% excess, determine the composition and the mass basis of the input and output streams. For the combustion reaction shown on this process flow diagram, determine the molar composition of the output stream if 100 kg per hour of methane are combusted in air. The fractional conversion for this combustion is 85%, and the air is fed at such a rate that there is a 20% excess based on the 100% conversion. Air composition is 21% of the oxygen and 79% more of the nitrogen on the molar basis. And the last problem that we will try to solve in the next tutorial: ethane is burnt with 50% excess air. The percent conversion of ethane is 90%. Of the ethane burnt, 25% reacts to form the carbon monoxide, and the balance reacts to form carbon dioxide. Calculate the molar composition of the flue gas on the dry basis and the mole ratio of water to dry stack gas.